like so that you have it. You know, you missed a lesson or whatever, and you just need a quick recap. And fast forward the living daylights out of it. All right. Anyway, so we got the whole scenario here. We got a mean. The scenario. The mean is given as 114.8 with a standard deviation for the population of 13.1. All right. If a woman, so a singular, so the A part, between these ages doesn't matter, all right, is selected at random, blah, 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 find the probability the systolic blood pressure is greater than 140. All right. So probability that X is greater than 140. All right. Singular individual selected at random. All right. That's a normal distribution question. We create our graph. We get our graphing calculator out. It glitches like 5 times, then it opens. We have 114 in the middle. Not quite in the middle. 0.8. So 114.8 plus 13.1x, go into the table, get our values all in one shot. Barely legible is okay. Just zoom in and just write it all in there. 88.6. 101.7. Light FM. 127.9. 141. And 154.1. All right, so bigger than 140 is right on the edge of what would be considered unusually high. All right. So 140 is just a shade below 2 standard deviations above the mean. All right. So statistically, it's showing up to be, it's not technically unusual, but it's close enough to unusual to be concerning because we don't want to have high blood pressure. All right. So now we do the math. The z-score corresponding with an x value of 140 would be 140 minus 114.8 divided by 13.1. Crunch those numbers. Oops, 140. 1.924, which is pretty close to 2. That's exactly, well, not exactly, but it's consistent with where I shaded, so we're in good shape there. So I need the probability that z is going to be greater than that number. All right. If you want a little bit more accuracy, instead of rounding this in your TI calculator, because I know we've been going back and forth between Desmos and TI, but we want to start learning a little bit more about TI. You can store this value as a dummy variable, right? So if you hit the store key, STO with the sideways arrow there, you can store it in as whatever you want. I'll call it A. So alpha math brings up the letter A, capital A. If you hit enter, anytime I hit A, that number would come up. All right, so this way I don't have to worry about retyping it over and over again. All right, so now going into second vars, looking for normal CDF option 2, my lower bound I could just put in, when I get there, I could just put in alpha math or the A value, and it'll know that it's going to be about 1.924. The upper bound, I just need something substantial, significantly, sufficiently large. Crunch it, and we get about 0.0272. So that storing option isn't always necessary. I mean, it's hardly ever necessary because we're rounding anyway. But if you're a little bit paranoid about accuracy, especially with something like this, you probably don't want to make a computational error. And, like why would somebody be testing a claim about systolic blood pressures? Probably because they work for a pharmaceutical company and they're developing blood pressure medicine, right? Now, that being said, you're probably not working with a TI-84 calculator in making those computations, but you would probably want to develop a more rigorous degree of accuracy, right? Something not just haphazard. Anyway, so 4 women in that age bracket are randomly selected to find a probability that their mean systolic blood pressure is greater than 140. So this is basically saying that if we wanted to create a random selection, that random selection wouldn't consist of just one person. It would consist of a cluster of 4 people. The probability that on average their blood pressures were above 140, that would be what we were looking for here. In terms of the importance of something like this, high blood pressure isn't contagious that I know of, but stress can be, So if you're trying to assess whether you're dealing with a very stressful environment, I cannot draw right now. Hold on. There we go. Then having statistical evidence that a cluster or a group of people are showing high systolic blood pressures or measures, that could be meaningful, very meaningful. All right. But it's a small sample. All right, so the n value is 4. That's the sample size. N is less than 30, so this is going to be a t distribution. Degrees of freedom is n minus 1. Poor quality minus sign. So in this case, 3. All right. But in terms of everything else, the mu sub x bar is still going to be equal to mu, which is still going to be equal to 114.8. The sigma sub x bar is still going to be sigma over the root of n, but sigma here, or sigma is still going to be 13.1, but the root of n would be the root of 4. All right. So you can leave it in that form if you want, although these numbers are going to be okay. So because it's just 13.1 divided by 2. Right. So is it 6.65? No, 6.55, right? I'll just do it. 6.55. All right, so we need to create a new scale for our distribution, which is going to be roughly symmetrical, is roughly bell-shaped, not necessarily the same shape as a normal distribution, but since we're just drawing rough sketches anyway, it really doesn't matter. All right, so 114.8, and I'm adding 6.55 to that. So back to my y equals, instead of 13.1, 6.55. Get our values. So again, 3 tick marks in either direction. Boom, boom, boom. Boom, boom, boom. So 95.15, 101.7, 108.25. All right. So these this is obviously an academic problem because the numbers are too nice, but you get the idea. So 121.35, 127.9, 134.45. All right, and again, we're looking for x being, or x bar in this case, being larger than 140. So that's going to be off the graph. All right. So we need the probability that x bar is going to be greater than 140. That's going to correspond to a z-score. All right. I'm sorry, t-score, because it's t-distribution. Same formula, though. X bar minus mu sub x bar over sigma sub x bar. 140 minus 114.8 over 6.55. What? All right, we could get this decimal value. We could also store it all in one shot. If you write it store as A, it'll give you the decimal and also store it as A, which I think is kind of cool. And it also sort of illustrates that it's off the grid, but you could also sort of fudge it a little bit and maybe just draw a little bit of shading here. So it's not that far off the grid. So maybe just a little bit of sliver of shading. All right. So about 3.847. So we got that. Now I just need to find the probability that t is going to be greater than that number. So second vars. Instead of normal CDF, it's t-CDF. Once you identify the distribution, a lot of the guesswork comes out of it. All right. And in fact, when we get down to, we'll learn about a chi-squared distribution before too long. And you'll see that there's a chi-squared CDF. All right. So identifying the distribution is going to be the name of the game, before, like I said, before too long. All right. So t-CDF. It asks you for the lower bound, which I stored in as A, but you could just type the decimal if you want. Upper bound, something sufficiently large. The degrees of freedom, which is n minus 1, all right, there is an n value of 4, minus 1 is 3, so 3 goes in for the degrees of freedom. Paste that bad boy and hit enter, and we're talking about 0.0155, approximately. All right. So that's, it's not too crazy in terms of process. You got that extra step. Really, if you think about what you're doing, aside from using a different distribution, a t distribution instead of a z distribution, the only thing that really differs is the presence of the n value, or causes a differing, is the presence of the n value, which influences your standard error. But everything else pretty much works the same way. It's incredibly tedious, but it's statistics. It's part of the fun. Reveling in the tedium.
When there's an n value in the question, that means we're doing the t distribution and not the z?
It could be a z distribution if the n value is bigger than 30.
It's also the same if it is equal to 30.
Oh, yeah, equal to 30 also, yeah. Very good. All right. So for C and D, it says 16 women in that age bracket are randomly selected. Find the probability that their mean systolic blood pressure is greater than 100 and less than 120. Sorry, I'm just going to get this and put it on a different page. I'll just save it, whatever. Oh, I could have done that. Well, what do you know? All right, whatever. So, C and D. So, 16 is the name of the game now. So, n is equal to 16. All right, and we want the probability that their mean systolic blood pressure is between 100 and 120? Oh, greater than less than, not equal. Doesn't amount to a difference, and we'll learn about why in about a week. We'll really get into the graphs of density functions, but for now, it's just believe me when I say. All right. So less than or equal or less than symbol are not going to amount to any difference in the probabilities. So what we're looking for again, diagram, labels, z-scores or t-scores depending on the situation. This is still a t-distribution. Conversions, probabilities, and so on. All right, so the graph. Can't do it. There we go. So 114.8. That's my mu, which is the same as my mu sub x bar. And my sigma, which is the same as sigma sub x bar, which is sigma over the square root of n, is going to be, I already forgot the number, 13.1, I believe, over the square root of 16 this time. So 13.1 divided by 4, talking about 3.275. So those would be the increments by which we label this bad boy up. All right, so to the calculator, 3.275x into the table. So 104.98, 108.25, 111.53, 118.08, 121.35, and 124.63. All right. So now this question didn't ask for the probability that the mean is greater than 140, but if you just consider that for a second, you could see that this is getting the distribution is getting tighter and tighter around the mean. So 140, when we had a sample size of 4, was definitely further away from the mean than when we had a sample size of 1. All right. And now it's really, really far away. All right. Again, not asking for that, but it's a safe assumption that the probability of getting 16 people selected at random who are all based off of these parameters, who are all suffering from hypertension, is very, very remote. All right. But this question is asking us for average values that are in the healthy range. All right. So they're in the range you want to be in. All right, 120 over 80 is the magic ratio, I think, if it even is a ratio. I don't even know, but those are the numbers that you want. So 120 being on the high side of that interval here. So this seems to be like, okay, these are the numbers we want. So let's see what the probability is that we're going to be kind of living in healthy territory, I guess. So we have all these values. I need a t distribution with a degrees of freedom of 15. So again, t distribution. So I need the t value for when the x bar is equal to 100, and I need the t value for when the x bar is equal to 120. So 100 minus 114.8 over 3.275. And then same deal, but with the 120. There's only 2 computations that we need to make here, so it's like, all right, well, one, I'll just do it manually. You know, you could do it with like an equation or something like that, but it just seems a little overkill to do it that way. So the first one I'm going to store as A. And the second one, so second enter to bring up the previous computation, if you didn't know. 100 changes to a 120 and make the A into a B, just so you don't have to worry about typing these values again. So alpha apps brings up a B, and now you have these two entries. So approximately negative 4.519 and approximately 1.588. So I'm looking for the probability that T is going to be in between these two numbers. All right, but I don't have to worry about typing those two numbers in again because it's going to get taken care of for me. All right, but storing is a pretty good feature on the TI calculator. Put that in there later. Yeah. Jeez, the whole world shows up. Yeah, I guess I really will do it later. All right, so second bars, TCDF option 6, going from A to B with 15 degrees of freedom.
Why the 15 degrees of freedom?
Because degrees of freedom is n minus 1, and we have a sample size of 16 in this case. 16 women selected at random. So. All right, so enter, about 0.933. So that's part C. Part D is the conclusion part of it. If a physician is giving a report stating that 4 women have a mean systolic blood pressure below 140, can she conclude that none of the women have hypertension or a blood pressure greater than 140? So that's one question that could be asked. There's other questions. You know, you start thinking about what the possibilities are. You know, what's the likelihood that a group of 4 people compared to 16 people would have hypertension, you know, things like that. You know, obviously, I would think that the more people you include with the group, the closer the group is going to have a mean value. I boxed myself in grammatically there. The group will have a closer mean value to the population mean. All right? But in this case, can we conclude that all 4 women have a blood pressure greater than 140? Well, no, because that's really not how averages work. All right? Because if you want to have, let's say, an average, you know, keep it simple, like you take 4 tests in a class and you want to have an average of a 90. You know, you don't have to get a 90 on every test. If you want to have an average above 90, you don't necessarily have to have every score be above a 90. It's just the case that you have to have, if you're going to have a score below a 90, you have to have something that's significantly above 90 to balance out the one that's below 90. All right. So you take 4 tests. You get utterly destroyed on the first one. You get like a 20, but you still want a 90 in the class. All right. Well, you get 90s on the 3 remaining tests. You're like, oh yeah, I did it. No, you didn't, because you never balanced out that 20. All right. So you would need to get like 160 on one of the other tests in order to balance that one out, assuming you're going only with 2 tests and the other 2 were 90s. You know, it is possible that you could only get, you know, like a couple of 140s and maybe just a 90 on another one. But you got to balance out that abomination of a 20, you know, like that disaster. Yeah, I mean, it happens to everybody at some point. You get just destroyed, and it's just annihilated, like just obliterated mathematically. Like you go into a test, you sit down, you look at it and say, I thought I knew some of this. I don't know any of it. Yeah. Now, hopefully this isn't a precursor for the next unit test, but I gotta say, you look at the work that I'm including for something like Part C here. It's a substantial amount. The .933 was almost like an afterthought. All right, so you got to be really careful here. I mean, yeah, you could get the right answer. There's a lot of stuff that'll happen behind the scenes that'll get you the right answer. But if you don't give me this stuff here, you're gonna have a problem. All right. So hopefully it won't be to the tune of a 20 on a test, but but it won't be pretty. I can tell you that. Obliteration, annihilation,
Demolished.
desolation, demolition.
One tab.
Will that test be during this quarter or next quarter?
Second marking period.
Okay,
Yeah, we're done with tests for the first quarter.
okay.
When does the first quarter end?